So thankfully the access database thing is out the door, and we don't need to talk about that anymore, so I can move on to something mildly more interesting, I guess. And we're going way back now to the radio controlled boat hydroplane thing. I actually had to watch my old videos on this because I'd completely forgotten where I was, what I was doing. So basically the last couple of things that we did were to kind of make some calculations and rough guesstimations about the sort of weight of the boat, and to put a stick in the ground on sort of sizes and the rough distribution of weight. So before I crack on and make a sort of first up design, the first thing I need to do next. So the first thing I need to do next is to figure out roughly what it's going to need to look like to float, which is kind of chicken and egg. So we're going to, again, same old thing with this exercise, a lot of it's going to be chicken and egg for a while. So what we can do is we can use Archimedes, one of Archimedes' principles, and he was a clever little bloke that discovered that roughly something will float if the amount of water it displaces weighs more than it does, and that's kind of a very rough thing about it. So basically, if the downward force, which basically is weight in this case, because we don't really have any other forces on it, is less than the upward force or buoyancy, then it will float. So yeah, I can sketch down a few little formulas so we can work out roughly what the volume needs to be of the boat with its given weight that we've kind of guessed. So it's all guesswork at the moment. Yeah, we can work out roughly what the submerged volume of the boat needs to be in order for it to weigh. So let's have a little look at some little thingamajigs. I need my glasses for this. So basically what we need to do is we've got an equal sign in the middle, and this basically means neutral buoyancy. So we need effectively the downward force to be equal to the upward force on this side for something to be neutrally buoyant, i.e. for it to just about float, not sink and not bob out of the surface of the water, which is unlikely, but we need it to be basically neutrally buoyant. And basically, how many times am I going to say basically? Right, the formula is for weight is mass multiplied by gravity. So we need that, the result of that, to equal the buoyancy force. And the buoyancy force is volume multiplied by the density of the liquid that it is in, multiplied by the force of gravity. So as you can see, so we've put those in brackets, as you can see we've got the force of gravity on both sides, so we can basically take out that and we're left with mass equals V times P, volume times the density of the water. So we can rearrange that a little bit and we can say that volume equals mass divided by P. So basically the volume that we're looking for, and this is the submerged volume, don't know why it's got an S on the end, volumes, yeah, that'll do. Submerged volume is equal to the mass, i.e. how much the thing weighs basically, divided by the density of the liquid it's in, which is water. So in our estimations we can then go down and say that volume, or the submerged volume, is equal to the mass, which we we guessed to be around about 2.3 or 14 kilograms, divided by the density of basically fresh water, which is most likely to be in, is 1,000 kilograms per meter cubed. That's an approximation, but yeah, it's good enough. It's very good enough. So what we can do is, and what I'll do is I'll pop over, because rather than doing all this by hand and with a calculator, we'll pop over to Excel and stick a few formulas in so we can play around with that and get some results. And so here we are, sort of jiggery pokery around the various bits and pieces here. So to run it through it again, it's basically, well, we don't need to run through Archimedes' principle, but so these are the little values that we're using and the units of measurement. So volume is V, which is in meters cubed. Fluid density, which is lowercase p in kilograms per meters cubed. Gravity force is, well, basically the speed of gravity, which is 9.8. This is fixed, by the way. Well, we're going to take it as fixed at this particular point on the planet. So we're going to say 9.81 meters per second squared, and mass is in kilograms. So we already guesstimated that the total mass of the boat is going to be 2,314 grams, or 2.314 kilos. The density of fresh water, like I mentioned, is 1,000 kilograms per meter cubed. And as we just mentioned a minute ago, the force of gravity, give or take a bit, is 9.81 meters per second squared. And these are little formulas that we were doing. And so we worked out that this results in 0.0023 meters cubed, or 2,314,000 millimeters cubed. So that is the volume, or the submerged volume, the amount of the boat, the amount of water that the submerged part of the boat will displace needs to be 2.3-ish million millimeters cubed. And the reason why I'm doing it in millimeters and not something easier like meters, or actually centimeters would probably be the easiest, is because basically all my design software is configured for millimeters, and that's what it gives me when it calculates volume. The things it gives me it in millimeters cubed. What I have done is I have decided, because we're going to start out with a very basic a very basic version of the design, because at this stage I don't want to spend ages making nice curved shapes on the floats, because it's going to need lots of modification. So at this point everything's going to be pretty square, so we can quickly draw it up, and we can get the volume of it, but we will then probably need to lose some of that by making it a little bit more aquadynamic. Is that a word? I don't know. But the water version of aerodynamic, we need to make it go through the water a bit better than a brick. So we will need to sort of shape it up a bit, which in the end will inevitably lose us some volume. So what I'm doing is I'm saying we're going to take off 15%, another sort of guess really plucked out of the air. We're going to take off 15% of our very basic shape in the eventual shape. So we're going to add the amount of volume that we need to account for that 15%. So we're going to stick a ballpark number in of 2,661,100 millimeters cubed to be the volume of the submerged part of the boat we're looking for. And that, in theory, should make it float. So let's get designing. Okay, so that's the numbers and the calculations out of the way for the minute. And now we can do something a little bit more enjoyable, like start the design. So basically what I've done here so far is in SolidWorks I have drawn out a little sketch, which I've put into the dimensions that we came up with a long time ago in the video aforementioned, where I kind of just stuck some sticks in the ground and said I want the overall length to be 700. And basically this line here from that point to that point represent the entire length. This point here is the middle of that 700, aka 350, and we've got the sort of bulk of the rear weight centered around 233 mil, or a third of the way along, and the remainder of the bulk of the equipment, at least it's going to be loaded on the thing, 2/3 of the way along at 550. Those are just relative distances between those two from the center line, nothing new there. We have a perfectly horizontal line here, and I've decided to, well, another guess really. To get the kind of attitude that I think it needs in the water, we're going to give it a 2-degree tilt up. So effectively this line here highlighted in orange, if you can just about see that, will be the top level of the boat, and it's going to be rising up 2 degrees between the back and the front will rise up 2 degrees. And that's the overall length. So if yeah, that's fine, we'll just get rid of that. I've also done a few other things here. So I've added a plane, which is the water line, which we can't see. There it is. So yeah, there's nothing interesting here. This is just a roughly where the water line would be in relation to the top of the boat, which this line represents. You can now ignore that line there entirely. That is just a horizontal line to work from. This measurement here basically means nothing either. So then what I did is I created a float, a very basic float, and there it is there. And as you can see, probably just about it, yeah, there we go. You can see that this original sketch here with the 700 line is exactly the same dimensions as the float is, from the very tip at the front to the very rear. And I've given it some, and let's have a look at those a minute. Let's get rid of that underlying sketch and let's have a look at this one. Yes. Yeah, so here's the sketch. It's basically just filling out some of those little design lines that I created earlier. I've decided I've given it a height of 80 mil. That is 700, and a few basic angles here. There's nothing particularly interesting to see. This is just a very quick sketch, which, as you can see, we have then, what do you call it, extruded out, so that we have a sort of a rough shape of a, let's get rid of that plane there, the rough shape of one of the floats. As I mentioned a little bit earlier, I'm adding a sort of frig factor of, what was it, 15% that we're going to shave off of this, because obviously this is not particularly compulsive. This is not particularly conducive to gliding through the water very well, much like a brick. So we will have to sort of narrow and point the tip down later, and that will obviously reduce the volume that this takes up. But I'm not going to get into designing all of that in surfaces and making it look all gorgeous now until we know roughly what dimensions this thing needs to be, and that's what we are trying to get to at the minute, is just get an idea of exactly what we're looking at in terms of getting that volume that we measured. So the next thing that I did was, and let's, yeah, what's going on? I don't know. Anyway, so let's have a look at the next sketch I did. So that is this one here, and as you can see, it is the sort of center of the hull where some of the, well, all of the electronics are going to be in. The servos, the radio gear, and all that kind of malarkey will be in here. Now I intend to add the ballast to sort of beams running along the top of the floats here, so I can get them right to the front, but that is not really important at this stage. So yeah, again, fairly rough. The dimensions are fairly meaningless. I've just plucked them out of the air. I've given it a little bit more angle at the front here, so that is out of the water. The idea is that, you know, only a part of this should be in the water when it's stationary, and because it's quite wide, and this is only half of it, don't forget, that section here that is underwater is going to provide quite a lot of buoyancy. So well, we'll see how it works out. Then what I did is, no, we'll discard that. Then what I did is, we're ignoring that for a minute, put that in, is I just simply mirrored it so that we have symmetrical. So I did that bit, and then just mirrored them either side, and that is approximately the shape that the boat's going to end up. Yeah, obviously we need to do a lot more work on it in terms of shaping, but we hope to get within that sort of, whatever it was, 2.6 million cubic millimeters of volume, so the thing will float. So then what I did is I've combined that together so that we've got one solid. and then bringing back this waterline plane a minute. So that's, and let's get a good view at the z-axis. So that's exactly where I really want the waterline to cut through. So as you can see, it's kind of high up on the front. It's not the, and let's do a little bit of a cut here. The other way around. Yep, that'll do. So you can see that in the, ooh, that's the wrong one. In the background, you can see, right, so this is the waterline, and you know, the back of this is only just dipping in. So the idea being is it provides buoyancy when the boat's stationary, and then when it starts shifting along the water, hopefully this angle here and these angles here and the general speed will pull it up out of the water and it'll start to plane. And this whole middle hull section will effectively be out of the water, I think. Maybe it'll be touching at the back, but certainly will provide much less drag than it would if it was all in the water. So let's bounce back out of that. We've got the whole thing. So that's where the waterline will be. So what I've done is I've going to make a cut all the way along the bottom of this structure, exactly where that waterline is. And basically cut it into lots of little pieces, and as you can see, it's now been sliced exactly where the waterline will be. This black line here that runs all the way around has sliced through the whole thing. So what we can now do is we can turn off certain parts of that. Not that one, not that one. Yeah, that one we can turn off. That one we can turn off. And that one we can turn off. So what we're left with is just the solid parts which will be submerged in the water when stationary. So if we highlight those three parts and go into the mass properties, we will see that the volume is 2.5 million cubic millimeters. So actually we're a little bit under what we wanted. What did we want? Let's have a look. Let's get the old spreadsheet back. We'll get there in a second. Powering it up, right. So we wanted, in reality, or not in reality, in the calculations we come up with 2.3 cubic millimeters, but I've added this shave factor on of 15%, which takes us up to 2.6 million. So actually, you know, pretty close actually. This in theory, well, this would, in theory, according to all the calculations, would work if we actually made it like this. The problem is that, well, I'm not going to leave it with all these pointy edges. We're going to shave off quite a bit here, probably a bit at the back, and just generally shave off some bits and pieces. And that's why I wanted, you know, that's why I was adding this 15% to the volume we require, so that when I lose probably about 15% from the volume, it'll still float. So yeah, I think what we'll do is, in order to increase that to 2.6, I will just slightly increase the depth at which this center hull section comes down, and I can just pop these back on like so. And if we go back to this one and look at the sketch, let's have a look at it straight on. If we increase that to, let's say, 55 millimeters, that's going to increase the amount of the center hull underneath the boat, and that is quite a big area. Oops, it's quite a big area, especially once we double the width of it. So that should provide quite a lot of extra submerged volume. So let's have a look again. Let's turn that one off. Actually, let's not bother with that. Yeah, no, we do need to do this. Sorry. Turn that off. Turn that off. Turn that off. Highlight. What else we got here then? Highlight that, that, and that. And let's get the mass now. Where are we? 2.66. That'll do me. So that actually gives us just fractionally over the 2.661 million cubic millimeters. That will make this thing float. Now we can go in and get rid of this window and bring back all of this. And spend a little bit of time in actually shaping this thing properly, probably taking off, hopefully not more than 15% of the volume, and the thing will float. So now we can get around to making it look pretty. But yeah, that's for another time.